Hi, we are Team 24062, the Total Artificial Heart team. The Total Artificial Heart is a bridge to transplant device designed by our sponsor, Cannula. The current device has a few major problems that we are addressing with solutions through this project. My name is Safia Abdeslam. I am the team lead and a biomedical engineer. Let me introduce you to the rest of our team.
I'm Eric Navarro. I'm the mechanical lead. I'm a mechanical engineer.
I'm Logan Radomski. I'm the team's procurement lead and I'm a biomedical engineer.
I'm Lucas Young. I'm the verification validation lead and I am a biomedical engineer.
I'm Abigail Little. I'm the prototyping lead and I'm a mechanical engineer.
I'm Jesus Mata. I'm the biomedical interactions lead and I'm a biomedical engineer.
Syncardia is a Tucson-based company that specializes in the only FDA-approved total artificial heart. The total artificial heart is a bridge to transplant device that targets patients who need a heart but are waiting on a heart transplant list. It is surgically implanted as seen here and recreates the pumping of ventricles to drive blood by sending air from a pneumatic driver outside the body through a cannula and through the patient where it moves the diaphragm to replicate the pumping. Heart failure is projected to impact more than 8 million Americans by 2030 and 20 people die each day waiting for a heart and other vital organ. The total artificial heart helps give people a second chance at life and has helped prolong their quality of life.
We are collaborating with Syncardia engineers to design a novel cannula system as they issue 2 CAPAs, corrective and preventative action, on their current cannula system. We are also collaborating with their regulatory compliance frameworks to document any changes made to the current cannula to obtain FDA approval. The current cannula was created 40 years ago and is made of plastisol, which is PVC with plasticizer. It also has a spiral reinforcement that is too thick to span the entire length of the tube. Therefore, a hard 80 short D durometer connector piece is connecting with a much more flexible 70 short A tubing, which is causing cracking to occur at that point. Cracking is occurring after extended use, which is greater than 180 days, in which case patients have reported feeling unwell as less air pressure is supplied to the heart. Furthermore, through research of material change, we found that plastic aging contributes to cracking. So we have started a verification process which takes approximately 6 months and was not requested by our sponsor.
The team solution to cannula tearing must adhere to Syncardia's current cannula requirements. The cannula is part of a subsystem in a larger assembly, so any deviation from these requirements may result in incompatibilities with the total artificial heart system. The main requirements that the team tested for in this project were that the cannula shall withstand at least 18.1 kilograms of weight before any damage. The cannula shall also withstand at least 7 kilograms of pull force before decoupling from the pneumatic driver and 15 kilograms of pull force before decoupling from the total artificial heart. The cannula shall also tolerate 1 twist per foot of cannula before any damage to the cannula. To compete with Syncardia's spud stiff reinforcement, the cannula must also withstand at least 250,000 90-degree bending cycles before and after artificial aging.
Over the course of this project, 3 main designs have been explored. The first of these is a cannula made completely out of segmented polyurethane solution, a material made completely in-house at Syncardia and known for its high levels of strength and variable viscosity. However, during the prototyping process, we discovered that this design would not be viable on a large scale. Our second design, an external reinforcement sleeve, addresses the cracking at the distal end. By utilizing a durometer between that of the driveline connector and the cannula, the sleeve acts as a bridge between the two. This allows the stress experienced at the distal end to be shifted to a location of the cannula with reinforcement. This design is considered to be a temporary solution for Syncardia, and with the simple structure, any necessary modifications can be easily implemented. Our final design and long-term solution is modeled off of medical-grade catheters. This design addresses both the cracking and material aging. With a change in cannula material from plastisol to polyurethane and the reinforcement type from spiral to braided, these changes allow for a cannula with increased strength and resistance to material degradation and cracking without compromising the necessary flexibility.
A major portion of this project relied on simulations since prototyping would have been too expensive. We have completed a variety of simulations on SOLIDWORKS 360, testing our braided cannula design and the sleeve design. This allowed us to simulate how our prototypes would compare to the original design, which allowed us to then continue with ordering the braided cannula and producing our sleeves here at the AME building.
In order for a supplier to be able to provide FDA approvable medical cannulas, they need to be ISO 13485 certified. ISO 13485 is the standard for quality management systems for medical devices. Our team looked at over 60 different cannula manufacturers, and only 7 of them were ISO 13485 approved and had the capabilities to manufacture our cannulas. Our cannulas require special tooling in order to perform the polyurethane extrusion as well as braid the reinforcement wire. Our team faced several challenges throughout this custom tooling and manufacturing process, including long lead times, incorrect tooling that couldn't hold the necessary tolerances, and then a 4-week litigation debate over unclear wording over who owned intellectual property in the NDA. We overcame these challenges with constant communication between us and the supplier, and then with Syncardia's help, we worked to expedite the order of both the special tooling and the cannulas to receive them on our necessary schedule. One of our verification and validation tests required special test equipment to perform. Another company had previously done this work because they had the test rig. Our team worked to acquire this test rig from them, and we negotiated the cost of the test rig down from $86,000 to only $18,500 for Syncardia. We acquired this rig disassembled into multiple different sub-assemblies, and then we reassembled it on site at Syncardia. Our team also created the software that runs the rig, and it monitors the air pressure in the cannula, and it stops the rig and notifies us if the air pressure drops due to a cannula failure. From the current supplier, Syncardia's typical order quantity of 200 cannulas is $175 a piece. Our new design cannulas are only $105 a piece, which is 40% cheaper, saving Syncardia $14,000 per order and about $70,000 a year. Our team faced several challenges ordering our custom cannulas, including long lead times, special tooling that couldn't hold the correct tolerance, and a 4-week delay due to unclear wording over the ownership of intellectual property with the manufacturer. To counter this, our team created a design of experiments and a risk burn down plan in order to maintain our current schedule, which resulted in constant communication with the suppliers in order to ensure that we were on time frames, as well as expediting our special tooling and cannula production orders.
When conducting testing, our team used equipment to weigh down from the suspended weight testing and used an instron, mill, and our specialized testing rig in order to make sure our cannula meets all the requirements in order for it to sustain human life.
The cycle rig testing is a test that will determine whether our new designs have overall improved the durability of the cannula. 9 cannulas per testing group are put on a testing rig that will turn the cannulas 90 degrees in both directions until failure. Sleeve cannulas are still undergoing testing, and polyurethane cannulas will begin upon arrival. As it stands, the average of the sleeve cannulas have withstood 227,500 cycles, but we still have 3 sleeve cannulas that remain on the cycle rig. With the suspended weight, torque, aging, decoupling, and cycle rig testing in order to make sure we met all the requirements that Eric listed in the beginning of this video.
In order for Syncardia to use our new cannula design, we must undergo a design control process. In phase 0, this will be the project evaluation phase, where we made a change request and process evaluation, where we make sure our project is feasible and able to be accomplished. In addition to this change request and process evaluation, Syncardia did a regulatory assessment in order to make sure that all the regulatory aspects of this project are feasible. In phase 1, we did the design inputs. This consisted of making a design and development plan, a verification and validation plan, and doing any hazard analysis that can come from this new project. In phase 2, we completed some design outputs. These design outputs consisted of making the verification and validation protocols, drawings, and incoming inspection requirements, and many more other design outputs. And lastly, from our part of the design control process, we also started and are going to finish design verification and validation for the company.
To summarize, our novel cannula designs have reduced the potential for cannula cracking and the effects of aging to improve the total artificial heart, patient quality of life, and save lives. Through this process, we have learned valuable lessons to make us more well-rounded engineers and prepared us for our future endeavors.